So 4.2 is going to take us a couple days. We won't finish it this week. It's going to stretch out, so it'll take us a little bit to get through it. This is kind of a big deal. The first derivative test. This is kind of a main focus of a college. If you were taking this class in college, the first derivative test, kind of like the main thing of what you would learn. Once you'd learn derivatives, which we did first semester, now it's like, what do you do with derivatives? Okay, and it's this first derivative test. Okay. All right, so we're going to talk about what makes functions go up and what makes functions go down, increasing and decreasing intervals. All right, so let's take a look at this. We've seen this picture before, this graph, and what makes functions go up and what makes functions go down. So what I want to focus on first are these first 2 points right here. And I want to talk about, we know that they are both different kinds of maximums. One of them is a maximum that has a corner and a cusp. One of them is a maximum that just has a horizontal tangent. So they're both maximums. They're different in one's an absolute and the other is a local. So those are the things that are different. But what I want to focus on today is what's the same about both of them. Okay, so not necessarily, we've been looking at what's different about them, but I really want to focus on what is the same and what would be the true for any maximum on any place. So this is a max and this is a max. Different kinds of maxes, but what's the same? What is the function doing right before it gets to both of those maxes? Okay, on the side of the function over here, what is the function doing right before or as it approaches and gets close to those maxes? What direction is it going? It's going up. Okay, on both of them, it's going up. And then what is it doing right after it leaves the maximum? It's going down. Every maximum has that in common. That approaching it on the left, that the function will be going up, and approaching it on the right, or leaving it from the right, that the function would be going down. That is true for every maximum value. And that leads us to what is called the increasing and decreasing intervals. Okay, we know that if f prime equals 0, that means greater than 0. That means the derivative is greater than 0. Then that means that the function is increasing or going up. And we know that if f prime is less than 0, the derivative is less than 0. That means the slope is less than 0, and that means that the function is going down. So when a function changes from one to the other, when a function changes from increasing first, followed by decreasing, that will always be the identifier of a maximum. Let me see. Hang on one sec. Pause this. Okay. Okay, so what we're going to do is we're going to create, we've done this a little bit already. We did this with velocity. We made plus minus charts. And when we worked with velocity, we know that plus meant it was going up and minus meant it was going down. So we're going to do very much the same thing here. Your first step is always going to be step 1. Determine all the critical points. So you've been working on that for 3 days, on how to find your critical points and call them critical point A, critical point B, critical point C, whatever. Okay, you're going to get those from endpoints. You're going to get those from implied domain. You're going to get those from 1 over 0, and you're getting this from 0 over 1. So you've been practicing step 1 for 3 days now. Okay, now we're going to take those points that you just found, and we're going to break them up into intervals. Okay, see how it goes? You go x less than a, and then you go from a to b, and then you go from b to c, and then you go something greater than c. And what we're going to do is we're going to make an interval and find out, does it start with a plus? Or does it start with a minus? That's my question. We got to figure out what it does. And after that, we got to figure out, does it have a plus or does it have a minus? And we're going to do that for every interval. And the plus tells us when it's going up, and the minus will tell us when it's going down. And sometimes those signs will stay the same. Sometimes we're going to have a plus followed by another plus, and we won't get to minus till over here. Or maybe sometimes we're going to have it where the pattern is minus, then plus, and then it changes again. We're going to have all different combinations, and what we got to learn is what each combination means. And anytime it changes from one symbol to another, from a plus to a minus or a minus to a plus, it means something. Okay, so let me show you what that means, and we're going to practice that. Okay, where is the function increasing and where is it decreasing? All right, endpoints. So we got to start. Does this function have any endpoints? Does it have a closed interval? No. Okay, so my endpoints, I just say none. And if it doesn't have any endpoints, then what am I supposed to check from yesterday's lesson? Okay, well, I know it's 7th period, but we have to check implied domain. That would be the next thing. If there aren't any endpoints, then you have to check implied domain. Implied domain is you look for square roots, you look for denominators, and you look for logs. Okay, does my problem have any of those? Okay, Sydney's shaking her head, no. All right, so then we have none. Okay, critical points. Do I have any of those? Well, I'm going to do that by doing the derivative. So my derivative says, okay, f prime of x, and I take the derivative. So that'll be 6x squared minus 12. 6x squared minus 12 has 6 in common, and x squared is minus 2. And I'm going to take that, and I'm going to set it equal to 0, and I'm going to set it equal to 1 over 0. So we do the work, and we set it equal to 0. And we divide both sides by 6. And then we add 2. And then we square root, and we get plus or minus square root 2. So there's your critical points, the first 2 of them. Then you also got to check, okay, what about 6x squared minus 2 being set equal to 1 over 0? And we cross multiply, and we get nothing. All right, so we got 2 of them. In our chart, we start with the smaller one. So the smaller one is negative rad 2. So we start with x has to be less than negative rad 2. And then we leave rad 2, and we go up to the next critical point, which is positive rad 2. And then we leave positive rad 2, and there's no other critical points above that, beyond that. Okay, remember we've done this before. So now we want to pick some test points. Let's start with the middle one. What would be a great number to pick between negative 2 and positive 2? Pick 0, sure. It's a great, easy, random point. It could be anything. You could pick 1, you could pick negative 1, but 0 is right in the middle. So we're going to pick 0. We plug it back into our derivative here. If you put 0 in there, what do you get for an answer? Yeah, and I don't even care about the 12. I just care that she said the word negative. If I would pick a different number like the number 1, and I would plug the number 1 in there, I'd still get a negative answer. If I would pick a number like negative 1 and I would plug it in, I would still get a negative answer. So no matter what, ooh, I better write that in a different color. These answers will always be negative. If those answers are negative, that means the function is always going down. If those answers are negative, then the slope is always negative, and the function has to be going down. Negative values mean negative slope. Negative slope means the function is going down. All right, well, we started in the middle. We didn't have to start in the middle, but we did. Let's pick a number greater than rad 2. Any random number. Nate, pick me your favorite number bigger than rad 2. 2 is small. Oh, no, that's bigger. Good job. Okay, if you pick 2 and you put it into your derivative here, what do you get? And that's all I care about. He doesn't have to say, oh, I get positive and let me figure it out. Let's see, 2 squared. Okay, he doesn't have to, he just needs to figure out whether it starts with a positive or starts with negative. And this is going to be positive. And if that's positive, that positive value means the positive slope. The positive slope means the function goes up or is increasing. All right, and then we we'll do our other one, pick your favorite number that's less than negative rad 2, like negative 10 or something like that. And if you pick negative 10 and you put it into the derivative and you work it out, you get a positive again. Positive values mean positive slope. Positive slope means the function is going up. All right. So my function was going up, then it changed to going down, and then it switched back to going up again. Can you picture that in your head? The function was going up for a while, it changed to going down for a while, and then it changes back to going up again. Every time it changed direction, we got something. It changed direction, so we got a max. So when a positive slope changes to a negative slope, you get a max. Another change happened, and when that happens, we get a min. So when a negative slope changes to a positive slope, you get a min. That's the order. Positive change to negative corresponds to a max. Negative changing to positive corresponds to a min. All right, so that's your next slide. This is called the first derivative test. A local maximum occurs for f when the derivative changes from positive to negative. This phrase will be the answer to 50% of the problems. I'll say, find me a max and y. And the and y part is the and y, you say, because I saw the derivative change from positive to negative. And a local minimum does the reverse. So local minimum is when the derivative changes from negative to positive. All right, so let's just quick sketch some of these. A change from positive to negative could happen 3 ways. Okay, so this is the first option. It could be a corner. That changed from positive to negative slope. It could be a cusp. That changed from positive to negative slope. It could be a parabola. That changes from positive to negative slope. They all have maxes because they all change from positive to negative slope. A minimum could be the other 3. A minimum could be a corner. It could be a cusp. Or it could be a different parabola. And all of those have the commonality that they all change from negative slope to positive slope. That's always the answer to your question of why. Okay, so let's try that again. Describe the behavior without using a graph. So tell me when it's going up, tell me when it's going down, but don't look at a graph to do it. Okay, once again, I don't have any endpoints because there's no interval. Then I have to think about implied domain. And once again, in this problem, there is none because there's no denominators, no square roots, and no logarithms. So all I have to do is look for my critical points. So my critical points will be f prime of x. So let's work out the f prime of x. That works out to be 5x to the 4th minus 20x to the 3rd plus 15x to the 2nd. What do you notice all that problem has in common? Okay, x and 5. And not just x.
5.
And 5. And what else?
X squared.
X squared. Okay, so x squared, which leaves me with x squared minus 4x plus 3. That factors too. That factors into x minus 3x minus 1. And when I set that equal to 0, I get 3 different critical points. I get the critical point from 5x squared, which is x is 0. I get a critical point from x minus 3, which is x is 3. And I get a critical point from x minus 1, which is x is 1. So I get 3 different critical points for this. So I want to find out what's happening at these critical points and what's happening around the critical points. So what's happening at them and what's happening before and after them. So I'll take those 3 and I'm going to make my critical point chart for that. So I do them in order. 0 is the smallest, so I'll do x minus 0. Then 1 is the next size, so I'll go from 0 to 1. And then 3 is the next one, so I'll go 1 to 3. And then anything greater than 3. Now my job is to pick numbers that are in the intervals and then test them in the derivative. Always test them in the derivative. Don't test them back in the original function. That was what we did for absolutes. We're not doing that right now. Okay, we're testing them in the derivative function. Okay, Kiara, pick me a number less than 0. -1. Okay, she picked -1 and that works just fine. Okay, we're going to put it back into the derivative. I always think it's easiest to put it back into the last form of the derivative we had. So put -1 into those 3 sections. So if I put -1 into 5x squared, what will I get?
5.
Okay, which is positive, right? You don't even have to tell me the answer. Just tell me if it's positive or negative. Okay, if I put -1 into the first set of the parentheses, what do I get?
Negative.
Okay, and if I put -1 into the second set of parentheses, what do I get?
Negative.
All right, so you told me positive, negative, negative. What does that ultimately turn out to be? 2 negatives and a positive.
Positive.
Because 2 negatives make a positive, right? All right, so she didn't even have to work it out. She just needed to tell me that that turned out to be positive. Okay, Christine, pick me your favorite number between 0 and 1. She's picking a half. All right, let's do the same thing. So could you please plug a half into the same 3 places that Kira did? All right, when you plug a half into 5x squared, what do you get? A positive number. Okay, when you plug a half into x minus 3, what do you get? Half minus 3.
You get negative.
Okay, and when I plug a half into the third part, what do I get? A negative. All right, so ultimately you got the same thing. You got a positive and 2 negatives. So that means this section is positive. Okay, Nick, pick me your favorite number between 1 and 3. 2. Okay, let's do the same thing. Can you plug 2 into the first, second, and third sections? Okay, what do you get when you plug it into the first one? Okay, second one? Third one? Okay, so you got 2 positives and a negative. What's that? Okay, that's a negative. All right, so Sydney, pick something bigger than 3.
4.
Okay, and Lynn, can you plug that into these 3 things? When you plug it into the first part, what do you get? Second part? Third part. All right, so ultimately your answer will be okay. What those positives and negatives do is tell you that the function is, what direction the function is going. So Nate, what direction does the function start out going? Up. And then after 0, what does it do? Still goes up. And then after 1, what does it do? Oh, it just changed. And when it changes from going up to going down, what does that mean I have? Okay, great. So right here, we identify a local max at x is 1. All right, then the function's going to go down for a while. And then at 3, what's going to happen, Nate? It goes back up. So what have we found when it stops going down and switches and changes to going back up again? A local minimum. So right here, we have a local min at x is 3. So my function went up. It went up some more. Then it switched to going down, and then it switched to going back up again. Okay, so that is what the function is doing. Then if I said, hey, draw something that might do that, there's no wrong answer as long as you're going up and then up again and then down and then up. So maybe your graph would look like this. You go up and then you go up some more and then you switch to going down and then maybe you switch to go back up again. Okay, really there's no wrong answer as long as your graph does what it's supposed to do. All right, let's try another one. Okay, Leo, do I have any end points for this one? Yeah, is there an interval, a closed interval?
No.
No, okay, so no end points. Okay, Noah, how about implied domain? I'm sorry, I didn't hear that.
There's a denominator.
There is a denominator, so what's my problem with that?
Can't equal 0.
Okay, so my denominator can't equal 0. So x to the 4th can't be equal to 0. And when I take the 4th root of both sides, that means that x can't be equal to 0. So I have my first number. 0 is going to be on my chart somewhere. I also need to do my critical point, so I'll find my derivative. Okay, I already worked out the derivative, so we don't have to worry about that together. The derivative turns out to be negative 12 over x to the 5th. I've already worked that out. And I set that equal to 0 over 1, and I cross multiply, and I get nothing. And then I take negative 12, and I set it over x to the 5th, and I set it equal to 1 over 0, and I cross multiply that. And this time I get x is 0 again. So x is 0 showed up twice, so that's an important number. So I go to my chart, and 0 is the only number I have to think about. So I have x less than 0, x greater than 0. All right. Now I got to figure out if it's positive or negative. The derivative is positive or negative here. All right, so Jeffrey, pick me your favorite number that's smaller than 0.
-1.
Okay, plug that negative 1 back into this derivative here, the blue derivative.
It's -12.
Okay, if I plug negative 1 into the denominator,
So it's -12 over -1. That's 12.
oh, that's positive.
Yes.
Oh, okay, so that's different than what you just said. So this is a positive value. All right, and then if I pick my favorite number that is positive already, and I plug it in, negative 12 over a positive number, that's going to be negative. So I have a change from positive to negative. And every time a change from positive to negative happens, that means I have a local max at x is 0. Every time there's any kind of change, it's a local something. If there's no change, if it was negative and then it stayed negative, that's nothing. If it's positive and it stays positive, that's nothing. It's only if it changes from one to the other. Stop me if you have questions, okay? It's a lot the same. I'm trying to show you like one of every kind of question. All right, how about the next one? All right, does it have endpoints? Again, this one does not have endpoints because there's no interval. Implied domain. This one doesn't have implied domain. Even though it has a radical, what kind of radical is it? It's an odd one, so there's no implied domain. So I can go right to my critical points. And so I'll have f prime. Okay, and just to save us time, I've already done the derivative. Okay, so I'm just doing that to help us save time. So our derivative turns out to be 1 over 3 parentheses x plus 1 to the 2/3. Okay, I've already done it. I'm going to take that and I do my two things to it. I set it equal to 0 over 1. I cross multiply, and that gives me nothing. So I'm just saving us time because I've already done the work ahead of time because we don't need to spend our time doing that all the time. Okay, then I go back and I try it with 1 over 0, and I cross multiply that, and this time I do get an answer, and I get -1. All right, so -1 is my only critical point that showed up. So I'll have to split up my interval into x less than -1 and x greater than -1. And I need to figure out maybe what's going on here. All right, Sue, pick me your favorite number less than -1. -2. You guys are always so conservative. -100. Okay, it doesn't matter. It just has to be something less than -1. Okay, when I plug a -2, as Sue said, into this problem, what happens to the parentheses? Are they positive or negative? Okay, and then when I raise it to 2/3, what do I get? No, it's going to switch to positive because when you raise it to a 2/3, that's the same as squaring it. And squaring something always turns a negative into a positive. So it's going to take that negative and turn it into a positive. Then I take the over 3, and that's still a positive. And then I times it by 3, and that's still positive. And I divide by 1, and it's still positive. So the whole thing is still positive. All right, so that turned out to be positive. All right, Christine, favorite number greater than 1? 14. Okay. So Christine, when you put the 14 into the parentheses, what does it turn out to be? And when you square it, what does it turn out to be? And when you apply the over 3, okay, so everything turns out to be positive. What does that mean about this problem? If it was positive and stayed positive, what direction is this graph going? Up, and then it continues to do what? Keep going up. So what does that mean about maxes and mins? There aren't any. There are no maxes and no mins. Why? And your reason has to say the word change in it. Okay? Because there's no change. There's no change in the direction. There's no change in the slope. So there are no maxes or mins. If you want to say that there are a max or a min, you have to tell me where the change is happening. Okay, there is no change here, and so there is no local max or min because the derivative, which tells me the direction, okay, the derivative, quote unquote, direction, never changes. If I ask you to write something or explain something and you don't use the word change in your explanation, I can't give you full credit for it. You have to tell me either something changed or something didn't change. Okay, I have one more before I let you work for a little bit. All right, describe the behavior. Again, the behavior is going to be, is it going up? Is it going down? Do you have any local mins or maxes? All right. This whole lesson had no endpoints. The endpoints are going to come on the next lesson on 4.2b. Okay. Implied domain. This one, none again. Only because there's no denominator, no log, or no root. So my critical points. I have, once again, done the derivative for us. Okay, the derivative turns out to be negative 1 over 2e to the 0.5x. All right, when we cross multiply this to 0 over 1, we get nothing. When we try cross multiplying it to 1 over 0, and we cross multiply then, we get nothing. What does that mean there are none of? Well, there is a direction, but there's no critical points, which means my chart is not broken up into different sections. My chart is very simple. My chart is all real numbers. Okay, I don't have to break this up into a section less than something and a section greater than something. It's just all real numbers because there's no critical points. So I can literally pick any number in the world that I want and test it. Okay? All right. So Kiara, what's your Jersey number?
1.
Okay. We're going to check the number 1. All right, if we plug the number 1 into our derivative, because the numerator is negative, it's going to make my whole problem negative. And no matter if I checked any Jersey number or any number I can think of, I'd still get a negative number. So what does that tell you that this function has a direction of? This function always goes down. It never stops going down. It never changes going down. The function is always going down. So that's the direction. All right, so we say the function always decreases, or you can say going down if you want. And then you have to say because the derivative, and you could put in parentheses if you want, direction is always negative. Okay, that wraps up this first lesson. So I'm going to pause the recording right now and give us a chance to stretch and take a little bit of a break. All right, so you need your graphing calculator out for this second section, and we're going to do some endpoints, okay? All right, here we go. Just remember, everything we just talked about, I know it's only been like 5 minutes, but, okay? A max is when you change from positive to negative, and a min is when you change from negative back to positive again, all right? Okay. Now, is there another way to have a maximum? So we just did a local maximum occurs when a derivative changes from positive to negative. Or, all right, is there other places you can have maximums at? And the answer is yes, it can be at endpoints. Okay, so here's what happens. If the left side of the endpoint is followed by a negative derivative, that would count as a max. Or if the right endpoint is preceded, like right before it, by a positive derivative. Okay, you got to be able to picture that. A left endpoint followed by a negative derivative. So a negative derivative means I'm going in what direction? Down. Doesn't that look like a max to you? Okay, a left endpoint followed by negative derivative, or a right endpoint preceded, that means coming towards it, with a positive derivative. That is also a max. So those are 2 other ways you can have a max. The reverse is true for your mins. Okay, we already know that a minimum would occur when I change from negative to positive. But a minimum can also be when the left endpoint is followed by a positive derivative or preceded by a negative derivative. And it just sometimes helps to just draw it. A left endpoint followed by a positive derivative going up. So you know that you have a min here. Or a right endpoint preceded by a negative derivative. So here's my right endpoint, and that means coming towards it is a negative derivative. So that's also got to be a min because it's at the bottom. All right. So let's look at this function. This is probably one of the most brain-twisting things you're going to have to think about. This function is not a function at all. This function is representing a derivative. So you cannot think that this is a max because it's not. All right? That is no longer a max when you're looking at a derivative. So I got to teach you the best way to like scrunch up your brain and think about this differently. What I want you to do is color code your notes. Okay, could you please go to blue, let's say. And anything that's above the x-axis, let's code in blue. So that would be like this. And anything else that's above the x-axis, let's code in blue. We are making our divisions at the places where it crosses the x-axis. When you're looking at a derivative graph and not looking at a regular function, this is not a function. This is a derivative graph. They are different. So I got to teach you how to read a derivative graph. A derivative graph, the most important parts are the endpoints and the critical points. Okay, here is, you have one. So the same question you just asked yourself, endpoints, do I have any? Yes. Critical points, do I have any? And the critical points are here. This is how you read a derivative graph. So then you're going to split up your chart according to the endpoints and the critical points. So my endpoint was 0, split up to 3. And then 3 split up to, we're going to say that's 5.3-ish. And then everything greater than 5.3, and there's no more endpoint. It has nothing to do with the top that's at 1 or the bottom that's at 4. Okay, that's where people get tricked out. It only has to do with the endpoint and the critical points on the x-axis. And then we fill in the chart according to whether the section that connected those was above or below the x-axis. So because from 0 to 3, it is positive, I write positive. It's above the x-axis. It's in a quadrant that's up above. And also above 5.3, it was positive. It was above the x-axis. And then this is the only section that's below the x-axis, so that's negative. Once you have your chart filled out, I would almost really recommend you don't even look at the picture anymore so it doesn't throw you off. Just trust the chart to help you know if you have a local max or a local min. Okay, trust the chart to tell you. And so we see on our chart an endpoint here at 0 that is followed by a positive. Okay, an endpoint followed by a positive. Okay, do you remember what that makes? An endpoint followed by a direction that goes up. What would that be? It's not. Okay, think about it. Here, I am an endpoint. Okay, here I am. And after me, the direction goes up. So if I'm the endpoint, I'm sitting here and everything else is going up away from me. So what am I? I am a min. Okay, local. at x is 0. Okay, then my next chart tells me I'm changing from positive to negative. Do you remember what that is? You can look back at the other page if you want. What is it when it changes from positive to negative? And think about it in your head. Like, do it like positive means going up. Minimum or negative means going down. What does that have to be? It has to be a local max at x is 3. All right, then my chart changes again at 5.3. This time it changes from a negative to a positive. Okay, that means the direction was down and then it switched back to going up. So what's that? That's a local min. And is there an endpoint on the end?
Yes.
No, this one did not have another endpoint. Okay, look at the picture. There was no more endpoint. It just kind of kept going up. So I have a local min, a local max, a local min. Okay, this is going to take practice. Okay, we're just going to practice this. Okay, next graph. Most important points of the graph are endpoints and critical points. All right, does this graph have any endpoints? Does it stop anywhere?
Yeah.
I was trying to draw it so it stops right here. Okay, that's an endpoint. Okay, does the graph have other critical points where it's crossing the x-axis?
Yeah.
Yes. Okay, I've got, these are all critical points. Okay, the other one is not an endpoint because it's just heading up. I should have maybe drawn an arrow on it. Okay, so I need to set up my chart where these critical points and endpoints are. All right, so this is less than negative 0.8, actually 0.75, 0.75. And then it was negative 0.75 to 0.2. And then it was 0.2 to 1. And then it was 1 to 1.6. And then it stopped. And I think for me, it always really helps me to color the sections. I usually use blue for when it's above the x-axis. And I often use red for when it's below the x-axis. And my blue sections in my mind are my positive sections. And my red sections in my mind are my negative sections. So then when I go to my chart, I fill out positive, negative, positive, negative. Endpoint. Okay, positive changes to negative, negative changes to positive, positive changes to negative, endpoint. Once I've got that set, then I can answer all my questions. Because I know that every time a positive changes to a negative, I have a local max. And every time a negative changes to a positive, I have a local min. And I trust that every time a positive changes back to a negative again, I have a local max. And now I have an endpoint on the right side, which is preceded by a negative number, which means I have a local min again. Okay, an endpoint preceded by a negative. That means it's coming towards that point with a negative slope, and so it ends on a local min. You'll get the hang of it. Okay, you'll get the hang of it. But start with identifying what's important. The important parts are any endpoints and any places where it crosses the x-axis. Maybe even places where it's broken. okay, where it's discontinuous, like this next one. Okay, for this graph, again, it's a derivative graph that we're looking at. It does not have endpoints, and it never crosses the x-axis, but it is clearly a broken, discontinuous graph. Where is it discontinuous?
At 0.
At 0. Okay, we call that an asymptote. Okay, so it is discontinuous at 0. Okay, there's a brokenness here, which means that's the only place I have to split up my picture. And again, I always color above the x-axis in blue, below the x-axis in red. Blue means positive, red means negative, and I fill out my chart accordingly. Positive, negative. Which means when a positive changes to a negative in a derivative test, you have a local max at x is 0. All right, so let's just review. Fill in the blank. A function is increasing when the derivative is what? A function is increasing, which means the direction is going up.
Which means it's
When the derivative is positive. Good job, Sydney. Okay, increasing means the derivative is positive. Decreasing means the derivative is negative. And if it's changing from one to the other, then you have a local min or max. Okay, so if you're looking at this picture, what would you tell me are the most important points to start with?
the endpoint.
Okay, does it have endpoints? Yes, okay, has endpoints. Okay, and where else is important? Critical points, which are at -2, 1, and 4. And then I'm going to color code my stuff. Blue for above the x-axis, red for below the x-axis. Only when it changes colors do you have a local something. Only when it changes colors or at your endpoints. Okay, so you'd have to try turning this into a plus-minus chart or a positive-negative chart. You'll get good at it. You'll get good. See how it's even arrowed and identified right here? There's an arrow pointing to it. It's a local max. You'll get good at recognizing, oh, it's a local max because blue changed to red. It changed from above positive to below. Okay, blue changed to red, that has to be a local max. Or red changed to blue, that has to be a local min. You'll get really good at that. All right, but I want to talk with you about these endpoints out here. What's this endpoint? Okay, it's an endpoint followed by blue. That means an endpoint followed by positive. And any endpoint that's followed by positive, remember, I'm an endpoint, and from me is going positive slope. What does that mean I am? I have to be a min. Local. And the other endpoint over here, I am an endpoint preceded by positive. That means positives are coming up towards me. And so I am a local max. Okay, we're doing great. Okay, you know, I put the same picture on here twice, so you could probably skip the one and just look at the second one. All right, here we go. All right, Nick, most important numbers on here. You might have to zoom in and look at it. 0 is important.
-2 and 2.
-2 and 2 are important. Okay? Is this guy down here important? No. Not on a derivative graph, he's not. Is this guy over here important? No. Not on a derivative graph, he's not. I don't have to, and again, I know you'll be told this is a derivative graph. Okay? So, if you like the color coding technique, make the top parts, anything above the x-axis blue, make the bottom parts red. Where the color changes is where something important is happening. So is anything important happening at 0? No, no color is changing there. Okay? The red represents negative values. The negative values represent the function is going down. All that's happening is that this function goes down for a while, gets to 0. It might take a little pause and think about it a second, but then it decides to go back down again. Okay? Does not change its direction. So you will need to then start working on creating your own charts for this. You'll have a chart that says x less than -2. You'll have a chart that goes from -2 to 0. You'll have a chart that goes from 0 to 2. And you'll have a chart that goes greater than 2. There are no endpoints here. These are intended to be going up all the time. So you'll have positive above the x-axis, negative, followed by another negative, ending with a positive. The positive ones mean that the function is rising, going up, increasing. So this section right here is increasing. So is the section at the end, increasing. The section in the middle, both of them are decreasing. So in between them is a local max. And in between the other two is a local min. Because one's changing one from the other. Okay, so let's answer the 4 questions on the side. All right, so Noah, question 1 says, maybe over here in the black. Find the x coordinates where f has a local maximum. Tell me where f has a local maximum.
At -2.
Why?
Because it traces from a positive to
Okay, it. Don't use the word it. What?
the graph.
No, the graph doesn't. The derivative. Okay, use the word derivative and use the word change. I like change better than transfer. I understand what you're saying, but try to use the word change. So he would say the function has a local maximum at -2 because the derivative demonstrates a change from positive to negative. Okay, Nate, part B. B, local minimum. Complete the sentence. The function has a local minimum at...
The function has a local minimum at, is that -1?
Nope. This is not a graph of the function. This is a graph of the derivative. Kira, want to try it? Complete the sentence. The function has a local minimum at.
It would be up to,
Why?
because it's going from,
Not it.
the derivative is going from negative to positive.
It's changing from
Changing,
negative to positive. Right. All right, so we've identified the local minimum. We did it right here. We said it was a local minimum. Local minimum is happening at 2. Okay. Jeffrey, complete the sentence. The function is rising or increasing on... What interval?
Okay. No.
Okay, Sydney, the function is rising or increasing on which intervals?
X is less than -2, and 2 is less than X.
Because?
They're positive.
Because what?
The derivative is positive.
The derivative is positive. Okay, not the derivative is changing, but the derivative is positive. Okay, Sue, where are the intervals? Complete the sentence on which the function is falling or decreasing.
-2 to the 2. Because derivative is negative.
Got it. You got it. Because the derivative is negative. All right, let's try reading this graph for our last one. I'm going to have to modify your homework assignment, and that's fine. I'm going to take problems off. You should be glad. Okay. Okay, Nick, again, most important parts of the graph. You give me letters this time.
A, C,
A is important.
C,
C is important.
E,
E is important.
and G.
G is important. Anybody else? Is he missing anything? Sue?
I'm kind of curious, why is that?
Okay. Is F important? Okay. It's broken, right? Isn't F broken? Then that makes F important. Okay? Yeah, we've got an infinite brokenness here, so F is important as well. Okay? So yes, anytime you have an endpoint, which we don't have any endpoints, anytime you have an x crossing the x-axis, important, and any brokenness, important. Okay, if you like the color coding method, okay, it's totally up to you if you like it or not. Okay, so then we say x less than a, because Nick decided a was important. And then a to c, again, c is important. C to E, E is important. E to F, F is important. F to G, and greater than G. Notice I left out B and I left out D. Not important. They're there like to distract you. Okay, they're decoys. Those are not important. Okay, then if it helps you, blue for above the x-axis. So everything that's above the x-axis, maybe you write positive there. Positive. E to F, positive. F to G, positive. Okay, red for below the x-axis. So we write negative, we write negative, we write negative. All right, now I'm not going to give you the answers this time. I'm going to have you do it. Okay, Leo. Where does the function have a local maximum? Do you need some help?
C.
Say it again.
C.
C. Okay, why do you think it's C?
Because the relative is 100 from positive to negative.
Awesome. All right, he's right. He identified C as a local max because the derivative changed from positive to negative, and that's always a max. Okay? Are there any other maxes? Okay?
F?
F. Why?
Oh, wait. Just kidding.
Just kidding?
It's the same.
It's the same.
I wrote it wrong.
Right, okay. So it's not an F because F isn't changing. F is the same, positive and positive both sides. An 8?
Would it be G?
Okay, why?
Because it's changing positive to negative.
exactly, the derivative again. So we have a local max again. And the local max is happening there because the derivative changed from positive to negative. So any other changes are going to be the local mins. So we have a local min at A and another local min at E. So what's happening at F? Absolutely nothing. Okay, because F was not changing in any way. F was positive before, it's positive after, it's not demonstrating any kind of. All right, so then, Christine, the last question, C and D. What intervals will the function be rising? Rising meaning going up or increasing. A to C, okay, so that's a rising interval. And? All right, E to F and F to G, okay, because?
The derivative is above the x-axis.
All you have to say is,
It's positive.
that's all you gotta say. The derivative is positive. You don't have to be fancy about it because the derivative is positive. That's it. That is why it is rising and increasing. Okay, so then we have the opposite is true. Everything else would represent a decreasing or falling section of the graph. All right, you guys did a ton today. So we did two different things that used the same chart method. We used the chart method off of graphs. You always identify the endpoints and the critical points first. Whether you have an equation to work with, if you have an equation to work with, let me zoom back up here a minute, like this. Then you identify your endpoints and your critical points by hand, and you work it out, and you cross multiply. If you have a chart to work with, you identify your endpoints and your critical points off of your chart. So either way, you're getting endpoints and critical points. Sometimes it's from an equation, sometimes it's from a chart. Once you have those, you make your chart for it. If you have an equation, you have to test values so that you can put a plus or positive and negative in. If you have a graph, I think it's easier. You don't have to check values. You just have to look at it and see if it's above the x-axis or below. All right, and then make your determinations from there.